Well, a little bit of an update. I achieved um, one. I came close to achieving the various parts of my goal. Um, well, one part I came close to. I got double the wattage that I wanted, but I managed to get the voltage in proportion to the amperage by 1.5 to 1, which is pretty close to my target of 1.67 to 1. And then in the course of tweaking, I forgot where I was. I erased my documentation. I only keep one set on at a time, or available. But I managed to discover a new problem I was having, was trying to get my target wattage. And the problem was that anytime I made changes to the various components, their values, I would get an incremental step up or down surrounding my target by a huge amount. So the increment in question was 300 to 1. And I wanted to get in there that was in one direction 30 to 1, in the other direction it was 10 to 1. Right in the middle there, which is pretty close to the square root, basically, of 300 to 1. So, but I managed to see, I learned that I wasn't making use of all of my resources. Theoretically, okay, this is all the simulator. You know, I try to stay practical, and then I try to, that's the last step I try to do, is I clean it up, so to speak, by making it more practical, more buildable. So one of the things I made use of was my 4 capacitors, their equivalent series resistance. I was just had them at the standard 10 milliohms for a ceramic-based dielectrical, the dielectric of a capacitor. Well, when I increased the equivalent, first I increased the equivalent series resistance, and I decreased of the various coils, because I realized, no, wait a minute, I have them set to pretty much the same wire size, 29 versus 30. I mean, wait a minute, that's not the way I had it originally. These current coils and the 2 transfer coils were usually a very small gauge, like gauge 10, and then the main coils over here were equivalent. They had internal series resistance equivalent to making them maybe a gauge 30 or something. So what I did here was I found that if I increased these 2 massive coils of 40 henries each, massive, to a wire size of 60, to bring their internal series resistance up to about 125,000 ohms, and still keep them at 40 henries, that was a good thing. And then my 2 current coils at 2 microhenries and my 2 transfer coils in the rotor, well, they're not the rotor anymore. I used to call them the rotor. They're the transfer coils, 10% coupling coefficient between the transfer coils and these 4 coils over here. I brought their wire gauge down to 10, and then I went further. I went to the limit, which is pretty much 10 strands of 10 Aug wire, which produced the minimum, which is a 6.25 nano-ohms. And in my simulator that I'm using to vary it, I had to take it to 10. See, now this is 62.5 nano-ohms, but I had to take it to 10 milli, I believe. Whoopsie, wrong one. 10 milli. Nope, 1 milli, excuse me, to get the 6.25 nano-ohms. That's the limit. You go any further and it just stays at 6.25, so you really can't make. So this, a milli is going to be 10,000 times larger wire gauge size, but that doesn't, wire gauge number. Okay, because every, as I believe, I think it's, let's go back to, let's see, if we go back to 10, if I can remember the proportional relationships. So 62.5 at wire gauge 10 size versus 20 gauge. Right. So every 10 number of wire size changes the equivalent series resistance by a factor of 10. So to go from 10 to 1 milli, so to speak, wire size, that's 10,000 to 1, and that's 4 zeros. Oh, that's 10,000 times bigger wire. Or, yeah, bigger wire than from a 10 size. And that's kind of weird. But we can equivalent it by volume of copper. And I didn't do that, actually. I just multiplied by 10. Actually, it's 10,000. Oh, my God. See, now I don't know what the volume is. Let's go see what the volume is. Diameter, here we go. So 10 to 20, here's per 1,000 feet, the resistance is 1 ohm. When you get to 20, it's 10 ohms. So it's 10 to 1. Pretty straightforward. But now the diameter in inches is 0.1 versus 0.03. So that's 1/3. No. Yeah, well, it's 30% is what it is. So 30% change going up the number scale. Now, if we go down, we multiply by 33. Let's see if that's right. Here, it's roughly 1%. We go down to 20. It's more than 3 times. Yeah, right, more than 3 times. So it's a factor of about 3.2 in that case. And we multiply. Oh, that's 3. Oh, wait a minute. 3.18 factor. But then when we go to here, it's not 3. Ooh. Oh my God. No, it is 3. Oh, I see. Right. Yeah, it's about the same. Okay. 3.2-ish. So the diameter should go 3.2 to the 4th power, right? So we take 3.2 times its, oh shit, sorry, my Spanish is not so good. Here, we'll do it this way. 3.2 raised to the 4th power is about 105. So the diameter goes up by a factor of 105. Now if we have 0.1 inches, times 0.1, we end up with 10.5 inch diameter to the wire. That's a pretty hefty wire to wrap around. I should say that. 10.5 inch. Yeah, that's what I should say here. I'm going to have to change this to say 10.5 inches. A 10.5 inch diameter wire, basically, to give us this amount of resistance. Anywho, so I changed the series resistance of the coils, and then I was able to bring the spark gap ballast down to 1, you know. It's like, wow. Talk about not needing it anymore. Let's see what else. So I'll just show you the results that I got. So I was looking strictly at coil 2 as my yardstick, to a quick and dirty method to try to estimate what the watts would be if I took the trouble to do a longer analysis longer than 700 milliseconds. I didn't want to wait. I wanted fast reaction time so I could quickly go through my various choices. So I would just look at the peak-to-peak. So 900 volts peak-to-peak, and 52 hertz for these spiky wedge-shaped surges on coil number 2. All right, then in a 700 millisecond analysis. And then I got a wattage of 65.7, negative 65.7 thousand watts, which is very close to my target. But now, boo-hoo, my volts to amps ratio is 15.85 to 1, because I have 1.32 kilovolts versus 83.2 amps. And although that's maybe a little less than half of the amperage you would want in an electric car, and not a Tesla, all the other lower price spreads, the voltage is a little excessive. And then this was the circuit I took it off of, but I still have to make changes to the original. I'm in the middle of making some other change. I forget what it is. Maybe it's the same one. I think what I was doing, I have to create the input graphs, the input documentation. So I have all the documents, and then I can move on to making further tweaks to see if I can get exactly where I want it to be. So I think that's why this is in a state of readiness, ready to look at the output. So let's see what I was supposed to look at the let's see, the input for amperage. Yeah, RMS. This is RMS input amperage is the magic value is 22.7 nanoamps. 22.7 nanoamps, which is not bad. It's, you know, it's been in the nano department, relatively speaking, more or less. So that's not bad. And then, of course, the total wattage is going to be ridiculous. Let's see, times 3. So it'll be in the vicinity of 66 nano, which this scale won't be able to handle. 66 nano watts. Let's see, what if I do oh shoot, I lost it. There. Yeah, there. Oh, it's not 60, excuse me. It's 48.2 nanowatts. So that's not bad. Just a little under 50 nanowatts. So, I mean, you know, what's your coupling, I mean, your coefficient of performance for something like that, you know, it's ridiculous. It's ridiculous to even worry about over unity. Is it over unity? How could you be sure? Did you do your measurements right? Well, it's pretty straightforward. There's only one input and one area of output that I'm concerned about. So if we get our, let's see, where was the figure? Was it up here? No. Was it here? So we get out our trusty calculator, and we multiply. Go back to standard view. We multiply 65, 696. Well, let's put that in storage. I may have to do some. Alright, so this is 48.179. Whoopsies. Okay, 48.179. Now that's nano. Now what's nano? Milli, micro, nano. That's 9 zeros. So I divide by 1, 2, 3, 1, 2, 3, 1, 2, 3 zeros. And then I take the inversion, which is a lot, and then I multiply times the memory to get my coupling, or excuse me, I keep a different coefficient, not coupling, a coefficient of performance. So my guess is it'll take 12 zeros to reduce this down to a reasonable size. So let's divide by 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah, 1.36. 1 1/3. 1 1/3. Now that was 4 sets of zeros. So milli, no wait. Kilo, mega, mega, what comes after mega? Giga, tera. 1.36 tera to 1. You're worried about the gain? I'm not worried. So I'll have to write that in the schematic. Oh yeah, that's right. That's it. See, I needed to change another line of text. So 1.36 no. Tera to 1 coefficient of performance. How do you like that? How do you like your over unity? Well, I like it pretty good. No, that's too big a... well, I could split it right here. There you go. Oopsies. Got in the way. Alright, that looks like a good spot to put it. So, there, I've documented that, so now I can change my schematic. So, anyway, moving right along. I better shut up now and go back to work.